The Agarwal-Gardner method, Agarwal and Gardner were research scientists at Amoco, which later became BP. And they did some work with production type curves as well. And they approached the problem from a pressure transient perspective and developed some type curves for long-term production analysis that were very similar to the existing pressure transient type curves that were out there. And they did some things very similar to what Blasingame did, but also looked at some slightly different ways of plotting the data and different ways of analyzing the data. For instance, we have rate versus time type curves similar to Blasingame, but we also had some cumulative production versus time type curves and rate versus cumulative production type curves. The work that Agarwal and Gardner did is all explained in their paper that was written in 1999. And a lot of the content that's in there is, a lot of the work that we've done is based on the content that was in the paper that they wrote. So let's talk a little bit about the ones that I want to focus on the most are the rate versus time type curves. And there is some comparison with what Blasingame does, but what Agarwal and Gardner did was a little bit different. So let's switch over here. I'll start by turning those ones off. In the Agarwal-Gardner format, we use dimensionless time that's based on area, rather than a dimensionless time that's based on Fetkovich's TDD, which is the dimensionless decline. So the shape of the curves is a little bit different. The underlying principles are the same. We still use a normalized rate. We still use a material balance time or material balance pseudo time. The process for doing the type curve matching is the same. We want to move the data around. And again, this is our boundary dominated flow example. So we would expect to get somewhat of a unique solution for gas in place when we match that data. Agarwal and Gardner have a derivative plot that's a little bit different. It's not the same as the Blasingame derivative, and it can show us some different things. Remember, type curve analysis is all about visual pattern recognition. So it helps to have different presentations of the data and get a sense for what's going on. One of the advantages to the Agarwal-Gardner method is it's very easy to see where the transition between transient and boundary dominated flow occurs. In a derivative plot, this happens right at the point where we have a convergence of the curves and it goes into the unit slope. There's a way that I can mark that location on the data, and I'll do that for you very quickly. You'll notice that some of the data points here turn blue. And I'm going to turn the derivative plot off so we can just focus on this plot. That portion where we have red data points turning into blue data points is our transition from transient to boundary dominated flow. So the Agarwal-Gardner boundary dominated flow diagnostic will indicate that point for us quite nicely. And I'm going to use my arrow pointer on here to physically mark the location of that point. And I can see it in my data as well. So in this data chart, I can show where that physically where that time to boundary dominated flow occurred. It may be surprising to you to see that it happened so early in time. On the type curves, it might not, almost looks like it's halfway through the data set. Remember, that's a logarithmic plot. In real time, that happened probably only about 2 weeks after the initial production. So the vast majority of this data set is boundary dominated flow. Another important thing I want to point out here is that identifying that point in time is always something that has to be done by looking back in time. In other words, I have to have enough data after that point that I can look back and see, okay, that's where it occurred. So it's always a back check, and I think I used the term earlier, a forensic analysis. The production data has occurred, and now I go back in time to see where we reached the boundaries. You can't do it just having the 2 weeks worth of data, or even 3 weeks or 4 weeks or 5 weeks. I need a lot of data past that point before I can go back and identify where that point took place. So identification of time to stabilization or time to boundary dominated flow is not something that can be done just on a day-by-day basis. I have to have lots of data, and then I got to go back and look at it and look at the whole shape and see where that occurred. Okay, so that's always sort of a tricky thing to identify where that's occurring. For instance, in that transient data set that we looked at, we may have reached boundary dominated flow, but we won't know until we've gone for long enough in time that we can see it having turned that corner, so to speak. And how much data you need past that point depends on how high or low permeability the system is and how large the reservoir is. If it's a low perm system in a very large reservoir, you may need years of data past that point to see it. If it's a high perm system, small reservoir, you may only need a few months or even less. Okay, so there's really a lot of factors that come into this. It's very important to analyze each well individually and try and get an understanding for what's going on. So the end result of Agarwal Gardner is it's just another method. It's very similar to blasting game. We should use both of them just to get a slightly different perspective on what's going on. But all in all, they should give you fairly similar results because they're using the same technology. The same theory behind each technique is the same. That's just a comparison of the derivative curves of each. The rate versus cumulative type curves that Agarwal Gardner have proposed, we ended up using those as the basis for our flowing material balance. So I'm going to come back to that one a little bit later on. I'm going to do one more thing here, and we'll go back to the software, and I'm going to show the NPI curves. And the NPI curves are really just Agarwal Gardner curves, but they're flipped upside down. And the purpose for this is nothing more, again, than just for a different visual perspective. Why do we want to flip them upside down? Well, if you're a pressure transient person, you're used to seeing data this way. So this is not a normalized rate analysis. This is a normalized pressure analysis. If you remember, normalized production rate is at Q over delta P. Well, we're going to look at, if we use the NPI method, we're going to look at delta P over Q. Okay, so NPI is the reverse. NPI, by the way, stands for normalized pressure integral. So it's work that Blasting Game did as well, but plotting the data as a pressure transient type plot rather than a rate transient type plot. And Agarwal and Gardner's method and NPI method are almost the same. They're just one's the reverse of the other. And I think that was the next discussion there. So I didn't need to spend too much time on that. I just wanted to make sure that we got across the point that those two are similar methods. They have identical plotting functions, except one's the reverse or the inverse of the other.